Hello, my darlings. Okay, so today we're going to talk about area between curves. Now, we have found the area between a curve and the x-axis. Remember, we did left ram approximations. We did rectangles, left ram, right ram, midpoint. We also did trapezoids, and we added them all up. And we said as the number of rectangles increased, the closer it came to the approximation of the actual area. Now, these little rectangles, and remember delta x was what we called the width of the bottom, but once we got to integrals, the delta x became your dx. It's the change in the x. And this was from a to b on the x-axis. This is our function y equals f of x. So we said that the area between the curve and the x-axis is the integral from a to b of f of x dx as long as the function is positive, okay? And that's the sum of the area of each vertical rectangle from x equals a to b. So we say that we use vertical strips. You'll understand why we're talking about vertical strips a little more in the next lesson. But vertical strips just mean that we're doing everything in terms of x, okay? We have dx, the change in x's, our function is written in terms of x, and we're integrating in terms of x. So we want to find the area between y equals f of x and y equals g of x on the interval from a to b, where f of x is bigger than g of x. It doesn't matter which one, we just have to assume one of them is bigger, okay? So the area between f of x and g of x is the area under f of x, so between f of x and the x-axis, minus the area under g of x. That would be the area between g of x and the x-axis, okay? Now, the way we do that, the area under f of x would be the integral from a to b of f of x dx, minus the area under g of x would be the integral from a to b of g of x dx. We can write that as one integral from a to b of f of x minus g of x dx. So when we're using vertical strips in terms of x, it's the integral from a to b of the top curve minus the bottom curve dx. So whenever we're integrating for area in terms of x, it's the top curve minus the bottom curve. So let's try one. So we want to find the area of the region between y equals secant squared x and y equals sine x from x equals 0 to x equals pi over 4. So that's that shaded area in there. So according to our rule, we will take the integral from a to b, so the integral from 0 to pi over 4 of the top curve is secant squared x minus the bottom curve is sine x dx. And here we go. The antiderivative of secant squared x is tan x minus the antiderivative of sine x is a negative cosine x. And we're evaluating from 0 to pi over 4. We substitute in the top limit pi over 4 first. So the tangent of pi over 4 plus the cosine of pi over 4 minus, now substitute in the lower limit, tangent of 0 plus the cosine of 0 equals, now the tangent of pi over 4 is 1 plus the cosine of pi over 4 is radical 2 over 2 minus the tangent of 0 is 0 plus the cosine of 0 is 1. So that's going to give us just radical 2 over 2 square units. And there we go. We found the area between the curves. Because remember, the integral from 0 to pi over 4 of secant squared x would give us all these vertical strips all the way down. And then when we subtract the sine x, we're cutting out this area, which leaves us just with the shaded yellow area that we want. Next problem, we want to find the area of the region between the graphs of f of x equals 14x plus x squared minus 2x cubed and g of x equals x squared minus 4x. Now, first thing we want to do is find the intersection of the two curves. So where do the two curves intersect? It looks like I can see it on the graph, but let's practice just in case. We know that this would mean that our two functions, x squared minus 4x, would have to equal 14x plus x squared minus 2x cubed. We're going to bring everything to the left side, so I'm going to have a positive 2x cubed. My x squareds are going to add to 0, and I'm going to have a negative 4x minus 14x, so that's minus 18x equals 0. I take out a common factor of 2x. That leaves me with x squared minus 9. So that's 2x times x plus 3 times x minus 3 equals 0. So our intersections are at 0, -3, and 3. So we have an intersection here at -3, an intersection here at 0, and an intersection here at 3. Now, why is this interesting? That's because when we find the area, remember the area is supposed to be the integral from a to b of the top curve minus the bottom curve. What's the top curve? Well, that's interesting because the top curve changes. In the pink region, the top curve is the x squared minus 4x, and the bottom curve is the 14x plus x squared minus 2x. But then they intersect at 0, and the top and bottom curves switch. That means we need two integrals to find this area. So the first integral is going to go from -3 to the point of intersection 0 of the top curve is g of x, which is the x squared minus 4x, minus the bottom curve, 14x plus x squared minus 2x cubed dx, plus the integral, now in the green region, goes from 0 to 3. The top curve is f of x, which is 14x plus x squared minus 2x cubed, minus the bottom curve, x squared minus 4x dx. Okay, so we have the integral from -3 to 0. Now I'm going to come over here for a minute, and we're going to do that subtraction. X squared minus 4x minus 14x plus x squared minus 2x cubed. We're going to distribute that negative into the second parentheses, so minus 14x minus x squared plus 2x cubed. The x squareds are going to add to 0. I'm going to have 2x cubes minus 18x. So there we go. 2x cubed minus 18x dx plus the integral from 0 to 3. Now this subtraction is just reversed, which means the answer is going to have the opposite signs, 18x minus 2x cubed. I don't care which order you write it in, dx. Now we're going to take the antiderivatives. The antiderivative of 2x cubed is 2x to the 4th over 4, or x to the 4th over 2, minus 18x squared over 2, or 9x squared, evaluated from -3 to 0, plus antiderivative of 18x is 9x squared, minus the antiderivative of 2x cubed is x to the 4th over 2. Notice the antiderivatives are the same, they're just different sign. Now we're going to substitute. When we substitute in the top limit 0, we're just going to get 0. Minus, now we're going to substitute in the -3. So we're going to have -3 to the 4th over 2 minus 9 times -3 squared, plus, now in the second set, we're going to plug in the 3, so 9 times 3 squared minus 3 to the 4th over 2, minus, we plug in 0, we're going to get 0. Okay, so what do we have here? The negation of -3 to the 4th is 81 over 2, minus 9 times 9 is 81, plus, and over here, we're going to have 81 minus 81 over 2. Okay, so -81 over 2 minus an 81 over 2 would be a -81 over 2, but we have a negative in front, so that's 81 over 2, plus 81 minus half of 81 is another half of 81. Add those up, we get 162 over 2, or just 81. And there we go. Okay, let's try another one. Sketch the region bounded by the graphs of y equals x squared plus 1. Now remember, x squared plus 1 is a parabola that hits the y-axis at 1 and opens upwards, and by the graph y equals 5. So that's the horizontal line, y equals 5. We are looking for the area in here. So the first thing we need to know is where do they intersect? Okay, so we can find our limits a to b. So if we take that x squared plus 1, set it equal to 5, that means x squared is 4, so x is positive and negative 2. So that's our region. Okay, now when we find the area, we can do the integral from -2 to 2 of the top curve is y equals 5 minus the bottom curve is x squared plus 1 dx. Or if you look at this graph, there is perfect symmetry over the x-axis, right? Because y equals x squared plus 1 is an even function. It's symmetric with respect to the x-axis. So by symmetry, we can say that the area is 2 times the integral from 0 to 2 of 5 minus x squared minus 1. I just distributed that negative. Okay. Now, is it necessary to do this? No, but sometimes it makes substituting in the values easier because it's easier to substitute 0 in than it is to substitute in a negative 2. It's totally up to you. Okay. But it is something good to know. So this is twice the integral from 0 to 2 of 4 minus x squared dx. Now, if I take my antiderivative, I keep my 2. Antiderivative of 4 is 4x. Antiderivative of x squared is x cubed over 3, and we're evaluating from 0 to 2. So that's going to give us 2 times. We substitute in the upper limit 2. 4 times 2 is 8, minus 2 cubed is 8 over 3, minus when we substitute in the 0, we're going to get 0. So that's going to give us 2 times, let's see, 8 would be 24 thirds minus 8 thirds. That's 16 thirds. But we have to double that, and it's 32 thirds. We have found the area between the two curves. Awesome. One more, and this one is a calculator question. Okay, so make sure you have your calculators. First thing we're going to do is we're going to graph them. In f1 of x, we're going to put 2 sine x. In f2 of x, we're going to put cosine 2x. So let's go. Let's graph it, find the points of intersections, and go from there. Okay, so here we are on a graph. In f1, we're going to put 2 sine x. And in f2, we're going to put cosine 2x. Okay, and I'm going to adjust my window and the window settings because we need to go from 0 to pi. And we'll make the y's go from, say, -3 to 3. And this is the graph that you're going to sketch on your paper where that x and y axis are. Next thing up is we're going to find our points of intersection. I want to find them both at the same time, so I'm going to do menu, geometry, points and lines, intersection, click on F1, click on F2, escape to get out of it. I now have my 2 points, but notice these are decimals, and they're also not out to 3 decimal places. So, a few things. I'm going to point at the first one. I'm going to control menu, and I'm going to store. I'm going to call the first variable, say, b, and enter. I'm going to do the same thing with the x value on the other point. I'm going to point at it. I'm going to control menu, and I'm going to store. This time I'll use C. The only reason I don't start at A is because we're using A for area, and then I just go across the keyboard. You can use whatever letters you want. I hit enter. Now you'll notice if I add a page and put a calculator page in, if I type B, there's the decimal. I type C, there's the decimal. Now remember, these are rounded. The calculator runs out of space. You are going to write on your paper underneath your graph, let B equal 0.37473443270 ... Let C equal 2.766858222088 ... Okay, so you should have your picture drawn, and we're going to write down, remember those points of intersection? We're going to let B equal 0.3747344. I ran out of space. And we're going to let C equal 2.7668582208 ... So, our area. When you look at the graph, first the cosine curve is on top and the sine curve is on bottom. Then the sine curve is on top and the cosine curve is on bottom. And then the cosine. So we're going to need 1, 2, 3 integrals. So here we go. Is the integral. Now from 0 to b. Which curve is on top? That's the cosine 2x minus the 2 sine x dx plus from b to c. That's 2 sine x minus cosine 2x dx plus the integral from b to pi. We're going to use our template key. We're going to use the definite integral. We go from 0, tab, to that first point of intersection, which is called B, of, now the cosine curve was on top, and we put that in F2 of x, close it, minus, sine was in F1 of x, tab over, this is with respect to x, tab out of the integral, plus template key, definite integral. Now our next integral went from the first intersection at B, tab, to the next point of intersection, which is at C, tab. Now this time the sine curve was on top, so it's F1 of x minus the cosine curve, which is in F2. Now if you want to type in the sine and the cosine, that's absolutely fine also. Okay, x, tab over, and I'll do that maybe in the third integral, dx, tab out of it, plus, we go back to the template key, get the definite integral. This integral goes from that second intersection, 0, tab, to the end of our interval, which is pi, tab, and this time our cosine curve was on top. So this time, you know what, I'll write it as if the way we're going to write it on paper. Cosine of 2x, close that parentheses, minus 2 trig sine of x, tab over, dx, enter. And our answer is 4.807. There we go. Okay, so when you write this on paper, remember, you have to have the graph drawn because there are axes there. You need to make sure that you identify what your B and your C are, that's written down on the paper. Then you can use it through all parts of a free response. Write down the integral so that they know what they're doing. Remember, it has to be there in integral form, and then you can go right to your answer. And there we go. All right, guys, have a great day.